Dando continuidade às palestras do 27º Simpósio de Aplicações Operacionais em Área de Defesa, o próximo palestrante será o professor doutor Randy J. Jost, da Utah State University. Leitura do currículo resumido do professor doutor Randy J. Jost.
Dr. Randy J. Jost possui uma carreira de destaque na engenharia, com experiência em universidades, indústria, governo e Forças Armadas dos Estados Unidos. Doutor em engenharia elétrica pela University of Missouri Columbia, serviu como oficial da Força Aérea Norte-Americana por mais de 20 anos, chegando ao posto de tenente-coronel. Atuou em centros de pesquisa de referência como o Air Force Research Laboratory e o Defense Intelligence Agency, além de contribuir como gestor e consultor em organizações como SRE International, Johnson Controls, Ball Aerospace e o Space Dynamics Laboratory, da Universidade de Utah. Especialista em compatibilidade eletromagnética, assinaturas de sistemas aeroespaciais, sensores ópticos e de radar. O Dr. Jost é autor de diversos livros, capítulos e mais de 100 artigos técnicos em conferências nacionais e internacionais. Atualmente, é professor adjunto da Utah State University, consultor em EMC e eletromagnetismo, e ministra cursos especializados nas áreas de EMC, radar e sensores ópticos. Membro vitalício sênior do IEEE e ativo em várias de suas sociedades. Também integra associações internacionais como a Antenna Measurement Technique Association e Association of Old Crows e a SPIE.
Convidamos o professor Dr. Randy J. Jost para iniciar a palestra intitulada The Requirement for Systems Engineer when Developing AI, ML and Cognitive Systems.
Bom dia. Thank you for inviting me. I'm not sure what I can teach you today, but I'll give you a few thoughts and be sure that I don't stand between you and lunch, because that's the most important thing I can do today. So what I wanted to talk about today was a way of thinking. You've already heard several very good presentations on what we need to be doing, all of us that are concerned about how we go into space, what we do with space, as well as all the other activities that are associated with keeping our countries the way we'd like them to be. So this looks like kind of a strange title, and I apologize that I don't speak Portuguese other than about 3 or 4 words, but we'll give it a try here. So this presentation is essentially a way to think about stuff that you do every day. And for most of you who are in the military or support the military, you know how important those activities are. And it's what we do with the infrastructure that we have, how we build upon it, really determines what's going to be happening in the future. So I want to talk a little bit about systems engineering and a little bit about artificial intelligence and bring them together in a way that you may not have thought about, but you use all the time. And it's kind of a way of thinking. As pilots, as engineers, we tend to train ourselves to think certain ways. And for most of the time, that works very well for us. But sometimes we need to step out of that way in a conscious fashion to understand and look at things a little bit differently. So I want to talk about things like when we talk about artificial intelligence and machine learning and using those technologies to augment or assist our capabilities, we should ask ourselves questions along the way. How do we know that the systems we're working with will do what we want. If we think about flying, a lot of times, if you're a flight test engineer, you do all the flying in the general capabilities of your aircraft. But if you really want to know what that aircraft can do, you have to go to the corner cases. If you don't do that, then you don't have the information to know how far you can push things. Artificial intelligence is the same way. There's lots of capabilities, and people are rushing to use it in everything from making your electric toothbrush work better, smarter, faster, to thinking about having autonomous wingmen accompany aircraft into battle, or to accompany soldiers out into the field with drones and robotic technology. So sometimes we need to find out where things are going to fail. So one question we want to ask ourselves is, how do we test those systems, and what are we going to do to make sure that they'll do what we want when we want? Okay. Oh, sorry, could you put that back in there? So the idea is how can we maximize those technologies and get the most benefit out of them? And so an important way to do that is taking an attitude that failure is not always a bad thing. So I kind of call that winning through failure, or WTF, which has lots of associations with it, and they all work. And so I'm going to draw upon some examples from the military and academia and the aerospace and nuclear industries. Okay. All right, so systems engineering has been around a long time. It goes back, really, if you think about it, you probably didn't build the pyramids without a rudimentary understanding of system engineering. You had to get all of that material, you had to get all those people, you had to schedule things, design things, build things, see how they were going to work. But really in the modern days, systems engineering as starting to be a formal discipline or concept came around during World War II. And so various people have written about that and looked at the history of systems engineering. And one of the earliest uses of that term was in 1950, and there was a talk on that. The transition from World War II into the years afterwards was a very important period in the development of systems engineering, because along with that development of all the technology that came about in World War II, things like radar and military aircraft with advanced capabilities for the time, depended on people being able to build these systems. And when we talk about systems, we're not just talking about the objects that we have, but the supporting infrastructure around it. If you don't have that, then you don't get the capability that you really want. So the very first paper about system engineering was in 1956, and one of the things that they noted back then was that there wasn't any good definition of systems engineering, and to this day I think there are a multitude of definitions, and not all of them are good. The first textbook on the system was written back in this time frame. And I'll make all these slides available to you. There's references in the notes section and stuff like that, so they'll be available for download. In 1967, there was a report to the U.S. House of Representatives talking about systems engineering and how it's somewhat like an architecture. If you're a systems engineer, you have to envision a whole product. And that means not just the pieces, the materials, but some of the aesthetics around it. How does it interact with its environment? How does it interact with the people that will be using those things? And as we go through these slides, I emphasize a couple of things. And one of the things that this panel wrote was that many of these ideas develop best through experience. How do we gain experience in systems engineering? And you all already have the basis for that, as I'll talk about going forward. Okay, so this is the definition that the International Council on Systems Engineering uses. It's a transdisciplinary and integrative approach to enable the successful realization, use, and retirement of engineered systems. And so that looks like a definition that was written by a committee where everybody tried to get their piece in there. But what it is a holistic discipline. That is, it's something that integrates a lot of pieces. And so somehow we want to make complex systems work well with all of the interfaces and all the inputs so that we get the desired output of there. Okay, so I'm not going to read through all these. They'll be available later. But again, I want to point out a couple of things. Let's see if I can do this. It's interdisciplinary. You have to consider the entire life cycle. And it's about balancing trade-offs. But sometimes one of the hardest things about systems engineering or developing systems is understanding who the stakeholders are. And as we go through some of the things that are in this presentation and some of the other presentations you've already seen, we'll find out that some stakeholders get overlooked sometimes. And they, in the end, turn out to be some of the most important people that we need to work towards. Systems engineering is about getting all the requirements. If you don't have all the requirements, you are not going to deliver the product that the stakeholders want. Coming up with the architecture is very important because it literally sets the framework of everything that's going on. Verification and validation are extremely important because once you've finished your product, whether it's your magic electric toothbrush or a new aircraft or a spacecraft or a tank or a ship, you need to understand, again, what its limits are. Is it meeting all the requirements? And oh, by the way, were those the right requirements in the first place? And finally, we want to talk about, you want to understand the risk management. And for different people, they have different concepts of what risk is. And so getting that idea aligned all the way through is extremely important to get your final product. Let's see. Okay. Systems engineering is really important. We use it because things get more and more complex. And as we talk about taking concepts like electronic warfare, cybersecurity, space systems, ground systems, communication systems that tie them together, people systems that have to be trained and operating these complex systems, we need to understand that complexity rarely goes up linearly. It doesn't always scale in a nice way, but sometimes as we go up, we cross thresholds where there are jumps in the complexity in terms of what we have to deal with. System engineering helps ensure quality because you do all your analysis up front. And it helps improve efficiency. However, I will say that if using efficiency as the only criteria will cause you problems in the end. That is, sometimes you want to be inefficient. So, for instance, in the United States air traffic system, it used to be a lot more inefficient. Well, what did that mean? Well, they kept aircraft around in hangars at the airports and things like that. And they were just there. Well, that's inefficient because they're just sitting there. However, if you're the passenger late in the day and your plane breaks down and there's no other plane to replace that, then that efficiency of not having it there no longer looks that good to you. having that extra little bit, which is inefficient by some aspects, actually helps keep a little more flexibility in the system. So there are trade-offs that you have to think about sometimes. Systems engineering concepts have been around a long time. And when we're talking about artificial intelligence, and it seems like nowadays everybody's racing to get artificial intelligence embedded in stuff, to use it for lots of applications, and that's not necessarily a bad thing, but artificial intelligence is, in some respects, has been around a very long time in terms of how you define it. And when I was a graduate student, one of my projects was working on image analysis of lung tissue for medical systems. So there's actually been a lot of work over the past 40, 50 years on using artificial intelligence to address medical diagnostics. We worked on things like automatic outlining of tumors in a lung. And so the question is, well, what's good tissue and what's bad tissue, and how do you separate the two? How do you define that distinction between them that allows you to say, I want this here, I don't want that there, we got to get it out. So, but what's really made the difference is a lot of funding's been going into it because people are seeing it's an opportunity to make money, and there's been a lot of advances in hardware availability and cost. So if you think about the data centers and the advent of general processing unit chips, that has really enabled a large scale increase in the amount of hardware that's available to do the processing of algorithms for artificial intelligence for things like ChatGPT and large language models. Again, though, if you think about it from a large system standpoint, is that always a good thing? How much electricity does a data center use, and how do you allocate that versus the people that live around it, or what other uses that electricity could be going to, the heat, the cooling, all of that. So you have to think about that again in a larger system fashion. So to consider some of the impacts and challenges of deploying AI techniques in aerospace and other industries, we just briefly review some of the inhabitants of the AI zoo, because there's lots of different approaches and language that's getting tossed around there. More specifically, I'd like to define 4 aspects of artificial intelligence. It's artificial intelligence, generative AI, machine learning, and large language models. The whole idea is to clarify those terms a little bit so when we use them, we have a common language to talk about. And so we talk about artificial systems and each of cognitive, both in the traditional sense of artificial intelligence as well as cognitive systems, large language models, and generative AI. And really, they're all part of the same family in a fashion. They're just at different hierarchical levels. So when we talk about AI, we're talking about the whole broad overarching field, with cognitive systems being a more specialized approach within it. And generative AI is a modern subset of AI that focuses on context development or creation. And large language models are a type of generative AI specifically for text. And so here's just kind of a chart that looks at the scope of those 4 aspects of artificial intelligence, some of the goals that we get out of it, and the human interaction that is associated with it. And one of the things that we want to take away from it is that artificial intelligence in some respect was basically a rules-based type of situation. So you can go back to older software programs that presaged ChatGPT or anticipated it, where people would type queries into a computer and then they would get a response. And those responses were limited just by what had been put into the program at that time. And they responded just on the rules that were available there. And so there's what's known as the Turing test, and the question is, if I talk to someone, something through this terminal, can I determine whether that's a real person or not? And that's kind of what people have been working toward, is to get to a point where basically you have something that's a cognitive system, something that is very interactive and would respond just as another, and I hate to use the term rational because people aren't rational. They're rationalizing more than they're rational. But you want something that could actually replace or be used in place of a human for doing certain tasks. Generative AI is to take that one step further and say, can it actually come up with something new? And then finally, large language models, they're just based upon huge piles of data that is a predictive model that says, well, if all these words come along in this order with this kind of weighting, then the next word should be this. And so each of those has a place in the galaxy of putting things together in an AI system. And so a couple things that we want to determine or think about is, how do you test a non-deterministic, adaptive, evolving system? That is, you have training data, you put it in there, that's your starting point. If you're building an actual cognitive system or a learning system, how does it learn? What does it learn? Does it add 2 plus 2 and come up with 4, or maybe does it come up with 5? Well, it depends on the rules, but if you make it adaptive so it can change the rules to be more efficient, then will it always go in the direction that you want? So you need to think about that. You need to understand how dependent your systems are, your artificial intelligence systems, on the data that you use to train and update them. Nobody's ever repealed the old adage from the early days of computers that garbage in equals garbage out. That's just the way it works. And so, where did you get your data? Has somebody injected data in there which is going to cause your system to maybe drift over time in certain directions under certain circumstances? So if it's evolving constantly, it's not like you're going to put a checksum in there and say, oh, look, we're still okay. You know, data in is what the results are out. What's really important is the idea of interfaces. In systems engineering, we talk a lot about controlling an interface. Who's responsible on this side? Who's responsible on that side? Because when you don't do that, you have problems like this team is working in kilometers per second, this team's working in miles per hour, and they're working jointly on the same software that's going to send a Mars orbiter to Mars, or a lander, and oops, somewhere along the way, one person thought it was in this unit, one person thought it was in that unit, and you end up not having a successful landing. So you have to watch out that. That is one area where large language models may come in handy, is being able to provide a better interface between humans and the software systems by being able to negotiate that between that. So how do you go about integrating AI and machine learning into the arenas of aerospace cybersecurity, EW, radar, and other critical technology areas? So I've got a couple of examples here of knowledge domains that might be of interest to this group. And when we talk about a knowledge domain, we're talking about a large amorphous collection of information that is required to work in that particular arena. So when we talk about aerospace systems, we could use AI as an autonomous navigation system for a space rover, and we build in as many rules and our best understanding of the environment, and then we put as many sensors as we can that will tell us about the important things in the environment, and we allow that system to take those inputs and make decisions, which are basically following rules to operate under those circumstances. However, that isn't always good enough, and that's why there's still people going into space. So the idea is to come up with cognitive systems that would act like a human in the loop and be able to monitor flight control systems, and they could potentially be a co-pilot, or they might even be the pilot of an autonomous vehicle that accompanies you out into combat or for other types of missions. Not everything's around combat. If you need to do supply missions, if you need to do missions of moving people from point A to point B to enable logistics, having those kinds of systems can save you a lot of money in the long run. People are expensive when it comes to flying in terms of training, keeping them proficient, and keeping them alive. You can use generative AI for doing things like novel designs for aircraft, taking information on weight, stress, tolerances, and all those factors, and coming up with suggestions to assist designers in making a better aircraft. And finally, you might use large language models to help develop the documentation. It's amazing, but at the end of almost every program, there's a few givens that you know. One is that you're behind schedule, one is that you're over budget, and one is that, do you really need to test this? Because we've built stuff like this before, so isn't that good enough? And if you're doing things in onesies and twosies, no, it's not good enough. If you're making 1,000 of them, then again, there's that efficiency versus cost and benefit trade-off. The Starlink constellation that's being put up by SpaceX, it's estimated that over time they'll put up close to 43,000 satellites in that constellation. What that's going to do to orbital debris and things doesn't even bear thinking about. I'm an amateur astronomer and I already hate it because it puts streaks in my astrophotography and my observations. But they can probably afford to have a few mistakes or something along the way in terms of their aspect. But nobody around them can afford for them to have mistakes if they happen to bump into their next door neighbor. You know, and when you're putting a constellation up that basically allows you to walk across the entire orbit, that's not necessarily a good thing. And then other people are coming in also, like Kuiper project from Amazon, to repeat some of the same things. If we talk about cybersecurity, again, we can use different AI-based type of activities to do things. And this is one of those areas where there's the good and the bad. There's both sides of the coin. So you can use AI to monitor your tools, monitor your traffic, collect data, build up an information database. But then you've got cognitive systems that can look at what traffic is moving through your networks and determine, am I seeing anomalies? Are there things in here that don't match up with my expectations? What should I do about that? How do I adapt? How do I investigate those things and then maybe adapt to fix them? You've got generative AI, and what we find nowadays is when it comes to cybersecurity, anybody can be a hacker because you can go out and ask your computer to write up a virus, and that's been around for a while, but it's just gotten a whole lot more interesting. And so the good things that come with generative AI can have bad things that come with them also. But it can help you by developing threat sets of data and running it against your system to find out where the coffin corners are and make sure that as different things come into your network and your system, that your system can handle that. And then finally, large language models are used a lot by scammers. They collect data, scrape it off wherever, and then they tailor make a very appealing link, article, YouTube video, book, whatever, that lures you in so they can get more of your information. And finally, when we talk about EW, you can do a lot with EW, and there is a move toward cognitive EW in order to be able to respond to the speed of the modern battlefield. And various types of EW are being developed very quickly these days. For instance, you could come up with a cognitive system, again, to look at your data that's associated with your flight in your environment as you're going against a set of threats, and try to figure out in a real-time fashion, in an adaptive fashion, what frequencies can I use to communicate, maintain my capability while fending off bad interference, fending off jamming, and that sort of thing. And while large language models may not be used directly, they could help filter data sets to reduce the workload on the operators such that they have a better chance of picking up the true anomalous problems or threats that they have to deal with. So a person by the names of James Friet, he writes an article on LinkedIn on EW, and he put an article together called Cognitive Electronic Warfare. And in that article, he listed some of the challenges that have to be addressed in order to use AI for EW. And that includes coming up with high fidelity synthetic data. So this gets back to that case of if you have an adaptive system and you've scraped up data, where did that information come from? And how do you know it's not been corrupted? You need to be able to scale verification and validation from the weapons platform standpoint, whether you're a single aircraft all the way up to the fleet, whether it be a fleet of aircraft or ships or a large number of units maneuvering on the ground where you can interact with those people. You need to stress test your cognitive EW against adversarial AI-based measures. And then you've got the challenges of how do you integrate people and AI together so they work as a team and don't work against each other. And then can we come up with good rules that we can use in machine learning to work with our rules of engagement. So at this point, I want to depart a little bit and kind of bring these two threads together and talk about system engineering thinking. And so developing system engineer thinking is much like learning how to fly and staying proficient. So ways to learn how to use this are things like learning from nature. So birds have been flying much longer than people, and a lot of the early development in aircraft depended on people looking at those creatures and figuring how do they stay up there and go from point A to point B. Bats and dolphins have used sonar long before humans did. And one of the interesting things that was discovered after the fact, even though we knew they used echolocation, was the fact that bats actually FM modulate their signals. They shouldn't be able to have the resolution that they have with their little throats, and yet they can see much smaller insects than you would expect, and it's due to that extra pseudo bandwidth that you get from an FM modulated signal that's swept in frequency. We can learn from the past, and NASA, for instance, has a lessons learned database. The FAA in the United States sets up a system where pilots can anonymously report anomalies and issues that they have in their flying. And that encourages them to be honest about it so that you can collect good data, not biased data, or data that wouldn't be available because nobody wants to be the end result of shooting the messenger. And then you can learn from other people's mistakes. So I teach a course in mission design, and a couple of the lessons that we spend our time on are looking at notable failures, trying to learn from them, understand what caused it, what chain of events led to this outcome, and is there a way to deal with that? And so a couple of examples of those are the shuttle accidents, and these documents are available online and are actually enlightening reading. Unfortunately, we don't always learn from our mistakes until we've had them really driven into us. So we had a Challenger go out, and then we had the Columbia incident, and a lot of the things that caused the Columbia incident were left over still from the Challenger. NOAA Prime was a satellite that Lockheed Martin was building, and one day the workers came in, and when you build satellites, they sit on like a barbecue rotisserie so that you can angle them, rotate them, and be able to get to the various sides while you're assembling them. And so they come in on a Monday morning and they start tilting the spacecraft down so they can begin work, and then all of a sudden it falls to the ground. And there's pictures in the backup slides there, because I don't want to take time from your lunch. But the end result of that was obviously a big oops that cost $135 million to fix. And what was the cause? Well, turns out that in the name of efficiency, another group over the weekend had taken the bolts and nuts off the NOAA Prime satellite and taken them over to another room because they were expensive nuts. I mean, they're about yay big. And used them on that other system, but nobody wrote that down in the log. And then when people came in on Monday to start working on this other satellite, and they started lowering it, they assumed, because they left on Friday and everything was bolted down and the nuts were there, that they were still there, which they found out after about 15 degrees was not a true statement. And so the end result was a very expensive delay in the operation of that satellite, having to get it fixed, and all due to a failure to follow procedures, check documentation, and everybody hates documentation. I mean, you know, aircraft pilots and aircraft maintainers need to really appreciate each other, which means pilots need to give specific information to the maintainers. Maintainers need to operate on that. And if you pencil whip your way through checklists and reports, eventually it's going to catch up with you. And that applies to all kinds of fields. So for instance, if you don't test, and testing is so important, you end up with failures. So this was one of many of the failures that are listed in the NASA Lessons Learned Guide. And there are others just like this one, where somebody made an assumption, somebody didn't check, somebody didn't test to make sure that what they thought they had was actually what was there. And I've had from personal experience what happens when you don't do that or people don't update documentation. So I'll try to close here by starting talking about the paradox of mistakes. That is, to build a skill, you have to do things. You got to do it often enough and repeatedly without making mistakes that you form a habit, that you get muscle memory. They say it takes 10,000 hours to really learn a particular skill. However, making mistakes is the way you learn. That's the way we've evolved. And so the idea is, in the ideal world, you make mistakes early, often, get corrected, and don't make those mistakes again because you've learned. So the challenge is, how do you make enough mistakes to learn, but not too bad of a mistake, and do so in a controlled environment? And so a key quote that General Omar Bradley did said, "I learned that good judgment comes from experience and that experience grows out of mistakes." And you often hear in the military world, it's been said that if it's stupid and it works, it's not stupid. Well, actually it is stupid. It's an unwise choice, and you succeeded, but it still doesn't make it not a stupid thing. You just might have got lucky. So one of the rules in life that I try to live by is don't do stupid things. Think, understand, choose wisely. And I don't have any fancy animation, so I got this little video clip to...
You chose poor name.
So don't be that guy. And I say guy intentionally because it's been my experience women make better choices than men most of the time. So another thing to go along with making those mistakes and making that result useful is you need to consider complexity. So when you're moving from easy tasks to more complex tasks, again, that's not always a linear scaling process. So mastering a single checklist for takeoff or level and safe flight is not the same thing as mastering the Dash 1. You really need to think about it as I'm going from straight and level flying to maybe I'm going to acrobatics to maybe I'm going to be dealing with the corner cases. And in each case, you're jumping a level of complexity that's not a linear scale from the one before that. You can't have too much experience. Knowledge without experience is a collection of facts. That's the encyclopedia problem. And most of you are too young to remember encyclopedias back from my day. But you have all these books and it's got all this information. And the question you got to ask yourself was, how does this topic relate to that topic? Because those facts don't tell you that. They just give you facts. They give you inputs. Experience without knowledge is a shot in the dark. So really what you're looking for is wisdom. And to my definition of wisdom is knowledge coupled with experience. So not only do you know the right information, you know what to do with that information. You get lots of information when you're in pilot training, but when you get in a situation, what is the most relevant information? What is the information you need right that minute to address that specific instance or that problem? So the idea is you want to gain and keep gaining knowledge and integrating it with a variety of experiences. Okay, remember, the scariest words you'll ever hear coming out of the mouth of a second lieutenant are, in my experience. They don't have any experience. That's what they're there for. They're there to learn, to make mistakes early in their career and not make those mistakes again. They're there to gain experience. And then they might become useful captains and majors. Okay? Gaining experience is a safe way to make mistakes. So we use simulators a lot, very common for pilots. It works in other industries also. So not only do pilots work in simulators, but basically in almost every nuclear plant there is another control room there, and its sole purpose is to provide you an opportunity to practice all the different things that could happen and go wrong. There's a reason that simulator training is really hard sometimes. It's because you have to go to the worst cases, figure out how to overcome them, and use that information in order to gain the experience so that if a real life situation comes up, you know the right things to do or have the best chance of pulling it out. You can expand that idea of simulation to other areas. So there are other obvious areas in EW and radar and comm. For instance, red flag and green flag exercises in war games. How do you expand that to other issues? For instance, logistics and operations. Well, you can do tabletop scenarios, you can do exercises, but you need to keep pushing your knowledge and experience boundaries if you want to grow in terms of being an operator. Okay. So, and it's hard to understand what it is that gives you that experience. And so you're trying to acquire cognitive skills, and we don't, as people, understand that about ourselves very well. How are we going to do that with software? And so a question is just understanding what happened. There's a paper that I've referenced and will provide it to you by Lintern, and he said that some people think that humans have limited processing capacity and are error prone, and as a result we should seek to design humans out of the system. And to some extent that's true, but at the same time you can't design the people out of the system. He gives a contrasting viewpoint that systems work because people are part of that system, that they are in the loop. And there are things that humans can do that machines still can't do. So for instance, there was a report of an incident that happened in the first Gulf War in which a British warship, the HMS Gloucester, shot down an incoming Iraqi Silkworm missile with its own Sea Dart surface-to-air missiles. And Gloucester was in a group of other ships in the Gulf at the time, and they hadn't seen any missiles up to that point. They had encountered a lot of aircraft coming back from bombing runs over Iraq and Kuwait. So ostensibly, when you look at a radar return, if that's not your area, you see a lot of stuff there on the screen or being fed to the data processor. And sometimes those threats are not distinguishable again from your own aircraft or other gray area aircraft. And so in this case, the officer was looking at it, saw this, called it as a missile, used the defense system, and was able to knock it out of the air before it hit the ship. The whole incident lasted 90 seconds, which isn't a very long time to make critical decisions that affect you and everybody else. And so they were at least, they were initially concerned, well, did we get one of our own aircraft to knock it out of the sky? Well, it turned out when they checked in on it, it was a Silkworm missile. But the tactical officer says, I'm not sure why, I just knew it was a tactical missile and not one of our aircraft. And so they thought about it for several months trying to figure out what that was about. And so what was known within that scenario was that the Silkworm missiles and the Allied aircraft all had roughly about the same signature or the same level of return coming back, and they operated at similar speeds. But it was also known that they traveled at different altitudes, around 3,000 feet for the aircraft and about 1,000 feet for the missile, which makes sense. You want to bury yourself in the sea clutter to get as close as you can before you do a pop-up. But the resolution of the puzzle actually did lie in the altitude difference. The aircraft and missile became visible on the radar only when they emerged from the ground clutter as they crossed the coastline. And given its lower altitude, the missile was closer to the Gloucester when it first emerged from the ground clutter. So it differentiated itself from a data standpoint. So the tactical officer didn't know why, but he had gained enough experience with how the usual activity in the area was with returning aircraft that he saw an anomaly and correctly identified it as the missile. That's the thing that doesn't look like the others. And so experience really does matter. In contrast, in the Second World Gulf War, we were using Patriot missile systems to defend places. And unfortunately, a couple of Allied aircraft were destroyed by the Patriot system. And so they went in and looked at it, and they determined that the operating philosophy of the Patriot missile system did not match the conditions of this conflict. In contrast to what was on the Gloucester, the Patriot missile system was highly automated. And operators were trained to trust the system software, and they were not accorded the opportunity to develop cognitive skills specific to the conditions of that particular environment. And so when you want to gain efficiency, when you want to act faster, when you want to take people out of the loop and make it more of an automated system, you got to make sure that you understand the environment and the different data streams that are coming in and what they mean and how they play over into things. So to kind of wrap up, what keeps us from using system level thinking all the time? Part of the problem is evolution teaches us to focus on what's at hand versus the big picture. Errors are due to too much focus. And there have been aircraft that have gone down, and after the investigation, it turned out that the pilot or pilots were focusing on this small problem over here and remaining unaware of larger problems that were developing over here, but maybe developing more slowly because the indications they got led them in the wrong direction. And so the solution, as much as possible, is to evaluate all the inputs, rank order them as to importance, and address the immediate critical problem. And one of the things we see when we look at the cockpit is there is a lot of information. And so the design of the interface between the human and the system needs to put the most critical information, the most immediate information, right there where the person can focus on it and use it. Also, there's a conditioning from society that we don't want to make mistakes. Mistakes are wrong, and we don't want to make mistakes. But if you think about it, when we write up reports, we're writing our theses, dissertations for academics, after-action reports, we tend to accentuate the positive, and we tend to downplay the negative. And in fact, that's where some of the most useful information lies, knowing what went wrong and why, so it isn't repeated again. But if you focus on only on what went right, then you lose those opportunities to learn, to put that into your database, to build that into your rules. And so what that solution is it requires a shift in thinking, and that thinking shift has to start at the top. Normally we talk a lot about bottom-up fixing things, but this is one where it has to come from the top. And why is that? Because we get conditioned to a kill the messenger type of management style. Nobody likes failure, but it is a learning experience. I had a lieutenant colonel that I was working for, and his mantra was, I don't like surprises. I don't like good surprises. I don't like bad surprises. I just don't like surprises. I want to know everything. And if you do, then you as a decision maker, as a leader, have the input to make good experienced decisions. If somebody's cutting off half your information, you are not serving your commander well. So you have to step up and say, this is what I did and this is what was good, and oh, by the way, I have some aw shucks over here, and we all know that one aw shucks will wipe out 3 attaboys or more, but that's the way you have to do it. You have to be honest in your information flow. Okay? So seek out red team input, subject decisions to second or even third opinions. And then you need to learn to think the unthinkable. Determine causes and solutions. Put these into scenarios and tabletop exercises. Most of the problems that we see out there in the nuclear industry because somebody didn't think that something could happen. It's unthinkable that people could take box cutters, take over an airplane, and run it into a couple of buildings. Yet that's what happened on 9/11. Because nobody thought that that was possible. So nobody planned against it or protected against it. That's a hard thing to do, is to think the unthinkable, because we're used to thinking about the ordinary and the everyday. You need to understand chains of events and possible consequences, and what you want to do is break that chain to prevent disasters. There's so many examples of things out there where if somebody had just done X instead of Y, bad things wouldn't have happened. And you need to avoid information overload, which means sometimes we're going to have to pre-process information. So we do that with our satellites. A lot of times we'll do in situ processing to reduce data streams so that you get the most important stuff down and you get it down the fastest. And maybe other stuff comes a little bit later. Ideally, you can do a segmentation of the problem and an integration of the solution. So we need to understand the powers of good systems level thinking, and we should practice it consciously. That means in your day-to-day life, when you think about it, you know, when you're dealing with your family, what are all the inputs? What is the environment? What is the situation? How can I make good decisions at home, at work, on a day-to-day basis? You need to know the requirements that enable the goal and keep the big picture in mind. You know, that's when you see these documentaries of animals running around on the African veldt while there's a lion or a cheetah chasing them. That's because it's an evolutionary tactic that ensures overall survival. If you've got wildebeest going every which way, well, that lion has to make a decision. Well, which one do I go for? You know, they want the weak ones, they want the slow ones, so you try not to be weak, and it's like the old joke, you know, if a bear's chasing you, you just got to be faster than the slowest guy. You can use artificial intelligence and cognition to be a force or capability multiplier, but you got to do it smartly and understand what you're doing with it. Systems engineering thinking is a skill that can be acquired, and it depends on knowledge and experience, which is often gained in conjunction with making mistakes. And it's a perishable skill, just like flying is. You don't put somebody in a staff position and then put them in the cockpit after 5 years and say, go fly this mission. You give them a chance to retrain, to reacquire the mindset, those skills. So I've put some references in here. I highly recommend all of these books if you have time. If you don't, read the book by Johnson, The Secret of Apollo. It really lays out very well. All my students have to read that book and do a book report on it. It lays out systems management, systems engineering. And then any book by Henry Petrosky is good, but a couple of them are really good. And these 3 out of about a dozen or more of these written will help you understand that failure is not necessarily a bad thing. You want to avoid stupid failure, but you learn a lot from it. Here are some references for applying artificial intelligence, and I've kind of limited them or focused them on EW and aerospace systems and cognitive EW. But I'll have a sheet of other references that people can download if they wish. And then there's some additional slides. Hope I didn't go too far, but thank you very much for inviting me. I appreciate it. I hope this was worth your time. And let's go eat lunch. Obrigado.
Convidamos o vice-coordenador do Programa Pós-Graduação em Aplicações Operacionais do ITA, Tenente-Coronel Aviador Daniel Alberto Pamplona, a realizar a entrega de uma homenagem em agradecimento ao professor doutor Randy J. Jost.
Dr. Randy Ross, thank you so much on behalf of our audience. Thank you so much for sharing your knowledge, your thoughts, your insights in such an important topic as systems engineering, machine learning. I'm pretty sure people are willing to see your short course tomorrow in the afternoon. And while in Brazil, I hope you have a nice stay here and a safe come back home. Thank you so much.